Beginning with the charging port, here we have referred to the standardized SAE J1772-2009 CCS Type 1 model as advised by the Government of India.
Now, as the electric vehicle charges, let us dive deep into the functionalities of AIM-Care.
To demonstrate the entire EV charging process, we have miniaturized the complete system comprising of the electric vehicle module, the electric vehicle supply equipment, and our own AIM-Care, autonomous intelligent modular charging apparatus for roadway electrics.
For proper plug-in action of port, we designed and developed our own custom linear actuator with crank slider mechanism. It is actuated by a DC servo motor whose rotation is then converted into linear motion. Special bearings are used to smoothen the action.
It utilizes a specific connector design for both AC and DC charging. The connector includes provisions for power and signal pins for communication between the vehicle and the charging station. The AC charging voltage typically ranges from 100 volts to 240 volts, while the DC charging voltage can go up to 600 volts.
Our robotic manipulator is equipped with 5 degrees of freedom. In the scope of prototype, we have attained 2-axis navigation of end effector by taking 2 degrees of freedom for base rotation and 2 other degrees of freedom to orient them. The joints are designed and fitted with ball bearings to withstand axial load due to plug-in action. Robotic arm is specially designed to have embedded wiring inside the linkages. All the wires for actuators are passed from inside the cavity of arm. Electronic components are also kept in shielded casing and are easily accessible by just removing access panels. High torque DC servo motors are used for our application. The entirety of arm has been rapidly prototyped by using technology of 3D printing.
In this electronic circuit, a supply voltage of 220 volts AC is initially provided and a capacitor is employed for initial energy storage. A metal oxide varistor serves as overvoltage protection. The voltage is then rectified using a bridge rectifier, converting it into 310 volts DC. Subsequently, a L2269DI IC generates DC pulses at a frequency of 65 kHz, which are supplied to the transformer. The transformer output, approximately 19 volts and 3.4 amps of current, undergoes rectification through 2 sets of Schottky diodes and is stored in 2 capacitors, which transforms it into continuous DC, ultimately serving as the circuit's output. To power the robotic manipulator arm, a 2S 7.4 volts lithium polymer battery is employed, followed by a DC-DC buck converter featuring overcurrent protection, yielding a stable 5 volt output. This regulated voltage is then directed to the servo driver utilizing the I2C bus, effectively steering all the servo motors responsible for the precise movements of the robotic arm. Well, now the real question is, how shall the robotic arm know the presence of the EV?
For that, we are using computer vision by detecting the port by the help of an high-definition digital camera. The program is being run on our local computer now, but program is made flexible so that it can also be run on embedded single board computer like Raspberry Pi. The convolution neural network trained on over thousands of images of EV charging port under different lighting and environmental conditions make it reliable for port detection. 3D pose of robotic arm is being calculated with respect to transformed values of charging ports in the camera frame. The computer then sends command to microcontroller which utilizes I2C protocol to communicate with actuators of robotic arm. Hence, whenever the EV enters and camera detects the presence of port, the charger connects itself to the port. Upon completion of charging.
Oi! See, the charging has completed now.
It was about time. It now sends signal to the microcontroller which relays it to the computer for unplugging the robotic arm and moving it back to its home position. EV is signaled to exit the location. So now it can aim for another one so that we can take care of it.